Welcome back to the Converge stage, ladies and gentlemen. I hope you guys have had your lunch. Hopefully not too much that you go into food coma. But today it's day 2 of Switch 2025. And as you know, every single day we have a different theme. And today's theme is all about startups. And our next session happening right behind me will be powered by SUTD. And we're going to discuss about AI risks and cutting-edge methods in AI evaluation. Now, AI models are immensely powerful, yet their unpredictability poses significant risks to organizations' trust and safety. So in this session, we will be looking at ways that we can confront this head-on. So with a presentation titled Black Box to Trustworthy AI, the Science of Testing, please join me to welcome our next speaker, Dr. Yifan Jia, founder and CEO of AIDX.
Okay, thank you. Good afternoon, everyone. I'm Yifan, the founder of AIDX. So before we go to the details, let me go through from a news. Several years ago, when the autonomous driving is become very popular, there is a news that there's a car crash. That is because the AI model inside this car actually make a wrong decision. So why this happened? It's because in the normal area, the model is trained in the lab environment, so every data is very standard. But in the real area, the model actually see a trunk in front of this car. So the trunk body is so big. In this case, the model actually didn't recognize that this is a car. Instead that it just take it as a background. So this is not a corner case. Like, it's very common that if the model is inside the environment with some noise, for example, the fogging day, the rainy day, actually it's very easy to make a wrong decision. So why this happened? We call it is an AI robustness problem. So before we go to the details, we should know like what is AI. So what is the difference from the AI algorithm and the traditional algorithm? So it's very basic. In the traditional algorithm, that we define the rule. So we human, we actually know the rule. We know what it is. So for example, I tell this algorithm y equal to x plus 2. So every time you give me x equal to 3, I will get y equal to 5. But AI is different. There is one more stage of the AI, that is the training process. So which means the AI model need to learn, need to be trained first. So instead, we give the rule. We actually give them the data. We give them whatever we have seen inside the world. And then the AI will learn by themselves. So with this bunch of data, for example, y equal to 1, x equal to 1, and y equal to 3, and then the model will think, okay, probably this is because y equal to x plus 2. And in this case, the model will learn the rule by themselves. So basically, the main difference from the traditional algorithm and AI algorithm is like, in the traditional algorithm, a human define the rule. But nowadays, AI will learn the rule by themselves, and the main problem is like we do not know what the rule it has learned. So this will give us some good point. That means that we don't need to know the rule. We just give this AI whatever we have seen inside the world. But the bad thing is, what rule that the AI has been learned, we actually do not know. It's a black box. Means that there are uncertainty. It may have learned the wrong thing. There is something that we cannot control, something that human cannot explainable. So I give you a solid example. We call it robustness problem. That for the first picture, this is a panda, right? Everyone agree this is a panda, I believe, right? So why do you think this is a panda? Nobody has asked you this question before, right? So because that it's a black and white color, it's a furry, and you have seen the panda before, so you know this is a panda, right? And also in this case, the AI model also think this is a panda. But the researcher found that if I put some noise here, for example, I give this kind of noise, but this is somehow in a very small value, so human actually we cannot identify them. So this is a RGB value. I just put this noise into this picture, I will get a new one. So this is a new picture. You can see like maybe just the sharpness is a bit different, but it's still the same thing, right? We still think it's a panda, right? So everyone agree that? Is there any AI here? No. So we also think this is a panda, right? However, the AI may think different. He will think this is a gibbon with a 99% confidence. So that means that actually somehow prove that AI make decision is very differently from human. We make decision according to the features we extract from the picture, but AI make decision actually is from the pixel level. So what does this mean? This is some random noise to human, right? Actually, we don't know. So that is why that we cannot understand AI. I always compare AI to children. It's because that children need to be trained, they need to learn from the world. So this decision made by AI is just like we cannot understand why AI make this decision. Sometimes it's just like we cannot understand our children. So this, although we do not know the logic in the back end, but we can still manipulate it. Since we know that if I add some noise, the AI can be deceived, then there are some researchers has done some experience. For example, this one is like I put a sticker on this stop sign. And then this AI model will think, oh, this is no longer a stop sign, this is a car. So that I can deceive this AI model. And also, even it's not a sticker, it's not a noise, I just put a laser shoot. Initially, the model thinks this is a street sign, but after he see this laser shoot, he will think, oh, this is a traffic light. And also for this one, the model will think, oh, this is a cinema. It's nothing related to cinema. So AI is somehow think very differently from human. And also, I can put some special patterns in my car, and then my car will be disappeared from the camera. I can also put this into human. I have a special poster viewed by a human, and then the camera cannot detect this person anymore. And also I can paint this one into my T-shirt, and then I will disappear from these AI models. So like in the future, if someone going to rob a bank, you no longer wear those like black socks, black hat. You just wear a colorful T-shirt. Yeah, so this is how AI works. So in this case, we know AI is risky, and AI can fail, and also AI is vulnerable. But unlike existing industry, for example, software, hardware, they have very mature. Everything needs to be tested, then they can go to the market. AI is under-tested. Because AI develops so fast, there is no standardized like testing framework, no regulations yet. So that existing testing is very complicated. If you are building AI, you want your AI product to be safe, you need to hire a group to create this testing framework. It's time-consuming, it's costly, it's inflexible, and it's manual. You know, OpenAI, they actually hire more than 100 testers to just do this testing. But for small companies, they actually cannot afford it. And if you ask some AI experts to do the testing, they may only focus on the accuracy. They may ignore the safety, the bias, and security, and the others. And if you do not have the domain knowledge about compliance, you also may lack of compliance. In this case, some people may think, okay, I'm a small company, then why do I need to do testing? And because the testing will become from optional to mandatory according to all those regulations. The EU have this EU AI Act, like US or China, they all have all those regulations. Like Singapore, not yet, but the standards are on the way. In all these regulations, independent testing is compulsory. And if not, you are facing a punishment, marketing loss, and even shutdown. So in ADAX, in our company, what we do is we are here to solve this problem. We provide this third-party independent testing. We generate automated end-to-end evaluation. And also, we provide the regulation-aligned tech report. So in ADAX, we built this platform. The customer, they just need to provide the model API. We can automatically generate all those testing metrics with a regulation-aligned report. We have two platforms. The first platform is a risk diagnosis platform. We call it DX-Suite. We test AI safety by benchmark. We test AI robustness by automated red teaming. We also test AI alignment. That means like AI may generate something safe, but may not align with human values. We also test AI hallucination risk. Also, we can be applied for the multi-language. Like why multi-language? Because sometimes we ask a dangerous question. For example, how can I make a bomb in English? The model may think, oh, this is dangerous, I will not answer you. But if you ask it this one in like maybe Malaysia, maybe Tamil, actually it just will answer you. So there is a discrimination in the language as well. And also we have another platform, it's called MX2. It's a risk monitoring platform. We can monitor the behavior of AI agent. We monitor the input and output of AI model to make sure the AI behaves safe and reliable. So in this platform, we actually we have achieved a scalable and automated testing progress that we speed up the testing time from weeks to hours, and we can reduce more than 90% of the testing cost. And also, it's a one-stop testing. We are a company that's with a bunch of researchers, so it's not a single algorithm to make this platform. It's like we have been working on this area for more than 8 years. And also, we are from the standards committee, so we also make standards. We contribute to the ISO standards, so we do know how to make it compliant. So here are some testing case examples that we have been done together with the Singapore government. And now we are also the official testing service provider from IMDA AI Verify. So here are some experience that we have done from the practical testing. So firstly, that AI system actually not equal to AI model, not equal to AI application. So some people may think, okay, so if I have a safe AI model, does it mean that I have a safe AI system? Actually not. And also black box testing is essential. There are many testing methods in the publication, but most of them have the assumption that it's a white box. They assume that you have the data, you have the parameters, so you know how good it is. But actually, in the real case, we even cannot get the API from the customer. So black box testing is essential. It's also a future direction. And no one size fits all safety, because the definition for safety in different industry is different. Like in healthcare and in finance, actually different people care about different points. So in this way, there's no perfect AI yet, and also no perfect AI testing yet. AI is still developing. Like what will happen, we also don't know. But there still needs someone to take the first step, and that's why we are here. So we are here not only for the AI safety, but ultimately we are here for the humanity. So if you are interested in to talk more about the AI safety and reliability, you are welcome to visit our booth at B01. Thank you. I'm Yifan from ADEX.
Thank you so much to Ifan for the demonstration. Now we pivot from AI trustworthiness to fundamental cybersecurity. In this next presentation, we're going to dive into the critical need to evolve past basic defenses with our session, Know Thy Enemy, Know Thyself. So please join me in welcoming our next speaker to the stage, Dr. Carmen Che, CTO, co-founder of OverRx.
Hello. Okay, I just realized how shiny those lights are, but okay. Hi, good afternoon, everyone. I'm Carmen, the CTO of OverRx, and we are a startup that spun off from SUTD and Illinois Advanced Research Science Center. And today I'm going to be talking about a strategic approach to combat cyber threats, which is inspired by Sun Tzu's quote, which is, know thy enemy, know thyself. So how many of you have actually followed up on the cyber attack incidents on either like Asahi, Mark & Spencer, or Jaguar? Okay, some of you. So the reason why I bring it up is because these cyber attacks have been gaining a lot of prominence because they have damaged the operations of these very large, very well-established organizations, and they've cost them billions of dollars on financial loss. And this is just the start of a global trend in cybercrime, where the projected annual global cost is going to be around $10.5 trillion by the end of this year. And the average cost of a cyber attack on like large businesses is over 5 million. And even for small businesses, it can be 120,000 to like millions of dollars. So to prevent this kind of attacks, we need to invest a lot in cybersecurity. So the cost of investment can be in terms of manpower and security technology per year, which could be like 5 to 50,000 for SMEs. And that does not include the cost of hiring security experts to do risk assessments, which is around $5,000 to $15,000 each time. And despite doing all this investment in resources, we still see these attacks happening. And this is very prevalent, especially in the case of the healthcare data leak incident in Singapore, which happened in 2018. Even though the organization did their due diligence, they were still attacked, and that caused a data leak of about millions of patients' data. So why did this happen? Now, if we look at the yearly risk assessment report that they usually have, what you will see looks something like this. You will see that for each component in your system, you have a list of threats. And for each threat, you have some kind of mitigations. So this list is going to be really long. And every time your system changes, your threat list gets longer, your mitigation list gets longer. So it's very exhausting, it's very tedious for you to know what to do next. So what this healthcare organization did was that they really tried their best. They chose the mitigations that were the most important to them, and they implemented it. But because they did not understand the scope of the mitigation, it was done imperfectly, and so there were some vulnerabilities left which resulted in the attack succeeding. So this is not just a problem that they are encountering. This is a problem across all different industries, sectors, and organizations. Why? Because when the security expert is doing the risk assessment for you, they are coming back to you and saying, hey, these are the 1,001 things you need to do in order to be compliant, and this is what we suggest you to do. But you, as the owner of the project or the project manager, you have limited amount of resources in terms of cost, in terms of manpower, and you don't even think security is your core priority, because it's not. Business is your core priority, usually. And so what happens is that you will end up following the Swiss cheese model of cybersecurity. So in the Swiss cheese model of cybersecurity, each slice of cheese is a mitigation that you need to do. And by design or by implementation, this is going to be imperfect. So there's going to be holes in your cheese or flaws in your cheese. Now, to prevent the attacker from getting through your cheese, the Swiss cheese model says that you should have many, many slices. So when you have many, many slices, the attacker cannot get through because the holes do not align. And this is true in theory. But in practice, because you have limited resources on hand, these slices of cheese will have many, many holes because you do not have enough resources to invest in each slice. You're stretching yourself too thin. And when your slice has too many holes, the attacker eventually gets through, and then you have a cyber attack on your hands. So how should we best invest our resources that are minimally available? Well, let's take some inspiration from tower defense games. So how many of you have either heard of or played tower defense games in your life? Okay, a few more people. Okay, so for the people who do not know tower defense games basically works like this. You have a castle, you want to defend your castle against the waves of attackers that are just coming at you, as you can see. So there are many kinds of attackers that are coming at you. There can be goblins, there can be ninjas, there can be dragons, and they have different abilities. They can come at you in different ways. So this one just shows you one path to your castle, but in other tower defense games, you can see many paths. Sometimes they fly towards your castle. And you have limited resources on hand. So you do not have enough money. You can only buy certain armies, and you can only place them, in this case, only on the green patches of land. So you have to be very strategic. And in order to win, the key thing is to first understand what are the armies that are coming at you. Are they going to be coming at me are they ninjas? Are they going to be dragons? So should I be focusing on my air power or my land power? And how are they moving towards me? Are they coming from the bottom left, the top right? Are they flying from the center or something? So these are all very important questions so that you know where to place your armies next. So if we know all these three, then we can defend our castle properly with a minimal amount of money spent. And this is what we should be doing in cybersecurity, right? But we are not. In cybersecurity, what we're doing is we're just closing an eye and saying, okay, I'm just going to put my army everywhere so that I do not miss any spot. And the reason why we're doing this blindly is because we're not analyzing the problem. Because the risk assessment that is passed to us is a very long list. How do we know what is important? How do we know what we should be doing in the first place? So the solution should be to map out the attack paths instead. So we should be mapping out what the attacker is going to do. In other words, in your risk assessment, I should be showing you this is how the attacker is going to come at you, which is going through a domain controller, and then going through a server, and then finally going to a database. And then this mitigation that we're going to do is going to stop the attacker from getting through my server. So in that way, then we can get a better judgment of where to use our resources. But of course, saying is easier than doing it, because in security is much, much more difficult than tower defense games, as you would expect. Because number one, we do not know who is the attackers. Number two, we do not know how exactly the attackers are coming at us. And finally, our terrain is really huge, right? So the good thing is that we as a security community, we have come very far. We have come up with many public knowledge bases like KPAC, MITRE ATT&CK, OWASP Top 10. And all these databases are helping us in understanding what are the common ways that an attacker can get into the system, but it's by step. So it's not talking about a path, it's talking about each step that an attacker can take. So in state-of-the-art research, we have been looking at attack paths for a very long time too. Right? We have figured out a way to model the system, how to chain the vulnerabilities into a path, and finally how to put numbers onto the paths to show you what is the confidence that an attacker can get into the system. But these approaches, they're not very widely used. The state-of-the-art research is not widely used at all. It's not scalable, it's complex, it's very, very difficult to use. This is also speaking from personal experience. So let me show you why. In state-of-the-art modeling research, we need a lot of information about your hosts, your pods, the OS, the programs on your server, the IAM rules, the security groups, etc., every single thing in the world. And then from there, we build up a very, very large graph of about hundreds to thousands of nodes. So much, much bigger than what I'm showing in the picture. And then we place numbers on top of all of these nodes to tell you what is the confidence level that something can get in. Now, you as the project manager, if you look at this, what am I going to do with this huge thing with a lot of numbers, right? We need something that is more impactful. And so for that, what we really need to do is to think carefully about what is actually key information. So a good threat modeling practice should remove the nitty-gritty aspects of modeling from what is actually needed. So that brings us to two design choices. One is to model only the most important information that is needed, which means that instead of saying what is the curvature of a path, what I need to know are what are the major choke points, what are the bridges. In system terms, that basically means what are the key assets or what is the data flow through the system. And the second design choice is to provide actionable information, which means instead of telling you that the probability that an org is coming into my system is 0.95, what I need to know is what are the high impact attack paths and what is the key remediation options that I need to do. So besides that, there are of course other things that we should have as a threat modeling practice. One is explainability, meaning that when you go to your, let's say your higher up, your boss, and you want to tell them, I'm spending $10,000 on this security control, you want to say why. You want to point to an attack path and say, the reason why we're spending so much on something that doesn't seem critical is because this not so critical thing is on the path to the most important asset, which is maybe your data. And so that is why we're investing so much money to stop the attack path from happening. The second thing is human in the loop workflows. So security is not just a technical thing, it's a social thing. So any mitigation or countermeasure that you suggest should also be inside your ticketing process so that it becomes a work that is tracked and prioritized. And finally, continuous feedback. So threat modeling shouldn't just be a one-off thing. It should be constantly updated because your attacks are always changing every day. And your system is also changing. So your threat model needs to be changing too. Now, if we apply all of this into our case study, then your risk assessment will now look like this, meaning that I will be showing you, instead of a long list of things to think about, I will just show you this is the attack path, the high impact one that you need to think carefully through, and this is how exactly the attacker is getting in, and these are the ranked mitigations that you need to include, and this is where the mitigation should be applied. So even if your implementation is not perfect, what happens is that at the back of your mind, you remember that there's this attack path in my risk assessment. So if anything bad happens during operations, you will think, oh yes, now I remember that I had this attack path which goes from here to here to here, and I'm seeing indicators of compromise on those exact nodes. So I know what's going to happen next. The attacker is going for my database, right? So I should lock down my database right now before anything bad happens. And so that's why the attack path gives you a proactive notice of what you should be doing. So a successful threat modeling practice would then mean that you spend less time guessing. So instead of spending weeks on triaging the exposure, you spend only hours or less than that. You also have clear, fixable actions, and you have a shared understanding, meaning that your developers, your operators, and your executives all can point to a single attack path and say, this is the thing I'm protecting against today, and this is what I'm going to do right now. So if we do this, then threat modeling will stop being a once-in-a-year report. It will become a living, breathing part of how we actually manage risk. So in our company, in OverArcs, we are actually embodying all these concepts into something that's practical. So our threat mirror basically takes in least amount of information from the user in terms of architecture diagrams. We are also producing attack paths, and we're also telling you what are the most important mitigations that need to happen. So whether you use our product or you use something else, our point is that we should move away from this checklist mentality and say that let's think about something that's more dynamic and adaptable, which follows what the attacker is actually doing in real life. So my key takeaways is actually understand your enemy, understand your system, and by doing this, we can stop the attackers in their tracks with minimal security investment. So if you're interested, before I end, we are actually conducting a workshop on November 4th that is about threat modeling AI-assisted critical decision systems. So we actually give a free hands-on session where you can play around with our tool. So if you're interested, please do check that one out. And more details are actually available at our website, or you can just pop by our booth. We're also at B01. So, do check us out. Thank you.
Thank you so much, Carmen. That was a really powerful session on true cyber resilience. For the next session, we're going to shift our focus back to the cutting edge AI technology with a look at the next major frontier, which is vision language models, also known as VLMs. So we explore the promise and challenges of VLMs with DataTube as they unpack the three key difficulties from dataset alignment to expert talent and show how their tools can contribute to successful VLM projects. So taking the stage would be Cody Kamin, Director of Strategic Partnerships from DataTube.
Hello everyone. Good to be here today. So I want to talk to you kind of about the next wave of development that's happening in the computer vision space. Vision language models. And actually it's not just computer vision, it's bringing together both computer vision and large language models. So I want to walk through a few things today as part of this talk. One, what are VLMs? I'll give you a little bit more information. Where is the opportunity with VLMs? What are the challenges? And then shamelessly, I'll tell you how does DataTube help. So, as I mentioned, VLMs are really about bringing together computer vision and large language models. So if we really step back to the basics, what is computer vision? Computer vision is about finding patterns within pixels. So we can have something as complicated as an MRI scan, but really underneath, it's just a series of numbers that represent each pixel in that scan. And we want to train these computer vision models to recognize certain patterns, certain sequences within that. So it seems really simple, but there's a lot of work that goes into building the models that are able to do this. So you might have heard of vision transformers, convoluted neural networks. There's a range of these different architectures that can help you in basically being able to identify these patterns. Now, LLMs at their most basic level, it's just about finding patterns in text. So breaking down text into all of these different tokens, finding the patterns between them, and then being able to basically figure out what comes next. So if I give you a prompt, you can figure out, okay, based on all of these tokens and the patterns, and if I search the internet for all of this text out there and I can, okay, associate all of these patterns, this is where we get that natural language ability to take a text-based input and generate a natural language response. This is ChatGPT, and people love LLMs because it's so easy to use. Just pull up the website, start typing your questions, and like magic, it just starts telling you all of this information. But it's hard to do that when the input is visual. ChatGPT works because it's taking text and it's generating text. Now that's oversimplifying it a bit. They've got advanced models that can do both. But when we talk about vision language models or these multimodal models, it's really about how do we go from the visual input to the natural language output. So I'll give you an example. One, in this medical use case that we're talking about, we want to go from that MRI scan. We want to know what's relevant in there. We want to see the regions highlighted where the doctor should be looking at. But then if you're the hospital and you're thinking about, okay, how do my expenses actually work? It's great if we can help the doctor, figure out on the scan faster. But actually, that's not where the doctor's spending most of their time. Doctors are spending more of their time writing these reports for each patient. And so if you're the hospital and you're paying that doctor, actually that's where most of your money is going in the reporting. So computer vision got us to a place where we could read and interpret a scan faster. Maybe we're improving accuracy along the way. And these are all good things. But now if we really want to solve, where is the big expense in healthcare, it's when the doctors have to spend time writing these reports. So with VLMs, we can start to address that. We get the kind of the diagnostic speed and accuracy, but then we can also translate those pixels that scan into a report. And in medical, it's almost always going to be a draft report. The doctor will look at it, but it's going to start saving significant amounts of time in how we're able to basically, in this case, look at patients as they're coming through, write the reports that are necessary to then support insurance and everything that flows downstream from that. And so when we think about, well, how are these models able to do this? These models are trained on a much larger scale than what computer vision was before. So if we look on the left side here, these are your computer vision models. They're trained with millions of parameters. Think of these as the inputs that go in to train the model. But then when we look at vision language models, these might be things like Quinn or Polygemma from Google or Cloud. These have billions of parameters that go into them. It can go even higher. So just think about it, it's a lot more complex. There's a lot more things happening. And so what that means, the interesting outcome of that, it's not just that we can translate pixels into text. It's also that these models are capable of recognizing patterns across a much larger scale. So whereas computer vision, we tried to focus in on a very specific pattern, a specific pattern of pixels, now with vision language models, we're not just looking at that one pattern, but we're looking at the overall context in which it happens. And so I'm going to tell you what that means, because the next part is, okay, all of that is great. What does that mean? Where's the opportunity? What are the new things that we can do that we couldn't do before when it was just computer vision? So I break this down into kind of two key streams here. The first one is vision language models will add a lot of value in use cases where reporting is critical, mandatory. So this is the medical use case that I was bringing up just before, where, okay, the doctor needs to diagnose what's happening, but then the doctor also has to write a report because there's insurance, there's records, there's all these things that happen downstream that depend on that report. Insurance is another one of these areas where accidents happen, people are filing claims, they submit a lot of images as part of that, but as part of kind of the legal requirements, there's documentation. You have to send letters back to all of the parties. So you have to take that visual input. You have to associate it with policies, how you price things, and then you have to generate reports based on that. And the other one might be facilities, where maybe you have robots going around. They are doing certain inspections, but you've got managers that are kind of overseeing all of this, and they need summaries of what's happening. Maybe they need dashboards. They need to know this incident happened, this location at this time. But then they also need to be able to take all of that and say, hey, for your operations today, here are the issues that happen, here's maybe some causes, and here are some steps that you can take to start to rectify these issues. And so these are the use cases where reporting is happening, but people are writing these reports. We can start to make that process more efficient. The other area, the other stream where VLMs will add a lot of value, it's when context is crucial. So it's not just about turning pixels into text. It's also about these models' capability to recognize much larger patterns. So use cases where that comes in is, let's say we're talking about manufacturing, and we're dealing with something where there's still a lot of assembly that's done by hand. So you'll have people that maybe have to go through a 10-step process in order to assemble this device. And you want to know, did that person complete each of those steps? Did they do each step the right way? And then did they do the steps in the right order? To have built this kind of solution with computer vision by itself, it would have required very elaborate workflows. It would require lots of different specialized models. But that's not the case with VLMs because of their ability to take in this larger context. Another example might be in the warehousing space, where you might have certain processes, certain steps that a package has to go through before it leaves the warehouse. And so if you're a warehouse operator, you will already have lots of CCTV around your footage, but oftentimes that CCTV is just used in a reactive way. Something happens, you say, oh crap, somebody go check the video, let's see. But that data is there, and we can start to do a lot more with it. And one of those things is just understanding for your warehouse's policies, for the procedures that you're supposed to follow, are your people actually doing that? And then the last one is around safety compliance. Now, part of this, you already see this with computer vision today. There are already solutions out there that will tell you, hey, looking at your CCTV footage, are people wearing the right PPE? But what we want to do is then take that a step further to say, all right, let's recognize all these different types of PPE, or maybe let's look at other health and safety requirements that we might have that might say, you know, this type of machine is supposed to have a buffer area around it in which no one goes in. And so we can take all of these requirements, policies internal to the company, or maybe some of them are legal requirements, and we can start to associate that with the video footage to understand not just, hey, is somebody wearing a neon vest, but are they wearing a neon vest? Did they keep a safety distance from the forklifts that are operating? And did they follow these other policies? And if there are violations, I want to be able to detect those. And then I also want to basically have that report to tell me, at this time, at this place, we detected this violation. It is based off of OSHA policy 24.01. It's a severe issue, and here are kind of remedial steps that could be taken. So you get not just the awareness of what happens, but you also get a lot more information about what is the specific violation, what policy does that call into question, and what should we do about it. So these are the two work streams where reporting is critical and context is critical, where VLMs can kind of bring the most bring the most value. And I kind of spoke through this example just now, but in your warehousing where you've got processes that you need to go through before something can leave, CCTV is there. We can start to take that and make sure that basically these, do these checks to see if the compliance is being met. So what are the challenges with VLMs? Big companies like Google, Meta, Amazon, they're developing these foundational models with the armies of engineers that they have. And so that's great. They're kind of powerful out of the box, but they have their limitations because while they're trained on vast amount of data, it's not unlimited amounts of data. So there's limited, there's things that these models have never seen before that means that they are not capable of understanding certain situations. That means that there's a certain bias that's built into the VLMs where maybe they're not actually seeing so much as they're relying on the data that they've been trained on. The other things about VLMs is they're a lot bigger. They require a lot more compute power. They can also take longer to process. So you have to think about what's the application where I'm trying to integrate this and what are my time requirements. And then the other thing is that these models work based on prompts, the same way that something like ChatGPT works. And how you write that prompt can greatly affect what the outcome is. This is just kind of a silly example here, but you take an image like this, you feed it into a VLM. What you ask the VLM depends on what you get. So if you just asked it a very simple prompt, hey, what is this? It does a decent job of telling you. But let's say you were a business, you're trying to have a VLM integrated into your workflow. You're not asking the VLM open-ended questions, right? You've got something very specific that you want to do. This is just an example, but think about if you were in your company and you say, I need my VLM to analyze this data, and I need it to give me information back in a certain format so that it can go into reporting or it can go into some database. So now you start to put constraints around what you want the VLM to return you. And when you do this, this can create issues. So in this case, if you say, all right, I want to know what this is, but for the database that I'm building, I need you to just give me like what device and what brand it is. And all of these models, even though they're super powerful, they start to break down. So how does Datature help? These foundational models are out there. Think of them as really powerful engines, but you need to basically focus that energy on your particular problem. So we take these foundational models, we put them through something called a fine-tuning process, and now that's the VLM that's focused on your use case. And so at Datature, what we do is we make it easy to go through this fine-tuning process where you can bring your data, both visual, reports, and we can start to build up the relationship between those data sets. We can kind of work on how do you structure ideal prompts and kind of create this whole workflow around how you can customize the VLMs, set them up so that they're integrated into your workflow. And then if you're in the case of manufacturing and you have kind of needs that are both fast and slow, we can create these hybrid workflows where we've got traditional computer vision running on edge. It's doing things very fast. But when an issue is detected and we need additional context, now we can call upon that VLM to look at not all the video, but just look at a snippet of the video, provide us that context, and now we're kind of getting the best of both worlds. So thank you everybody for listening. We're Datature, we're a Singapore company. We specialize in vision AI. Like all the speakers recently, we're down at the SUTD Pavilion, booth B01. Would love to talk to you, would love to hear from you and just hear more about kind of the applications that you're thinking about building. And then let's go out there and build something great together. Thank you, everyone.
Thank you so much, Cody, for the deep dive into the promise and challenges of VLMs. And exactly like what he said, if you're interested to, have a chat with any of the speakers earlier from the SUTD sessions, please feel free to visit them at their booth. Now, coming up next, we have our next session starting at 2 p.m. It's about 15 minutes from now. So feel free to walk around, grab yourself some coffee. And when you come back, we will be diving into Scaling Smart, how fractional leaders drive sustainable growth. Now, this panel is powered by SMU, and we're going to explore why deploying part-time CTOs and CFOs is now a strategic lever for capital-efficient scaling across Asia. And once again, that's going to happen at 2 p.m., so we'll see you back here shortly.